You and a friend have been imprisoned for your crimes against math, but luckily the warden also loves math and promises freedom if the two of you can solve this puzzle. There's an 8x8 board full of coins, all either heads or tails. One of the squares on the board hides a key. The first person, or player 1, gets to know where the key is hiding, but only gets to flip one single coin. The second person, or player 2, must then guess where the key lies without knowing which coin was flipped or anything else other than what's on the board. The two of you can strategize beforehand, but during the puzzle, you will be led into a room one at a time to prevent any communication other than through the board itself. The solution to this puzzle is a little bit tricky, but if you want to try your hand at this, pause the video now. If you've given it some thought, you probably have an idea what the shape of the solution should be, even if you don't know the specifics. To start, all of the information on the board, whether this coin is heads or that coin is tails, through some algorithm, must deterministically encode a particular location on the board. Call it the encoded square. Second, you should be able to move the encoded square to any other square with just a single coin flip. This way, you can move the encoded square to the key square. Third, even if you're player 2 and don't know which coin was flipped, you should be able to apply the algorithm and get that same moved encoded square. Lastly, your solution should ideally still work for smaller board sizes. Without further ado, here's my solution. We'll start with the 4-square version of this puzzle. Start by numbering each square 0, 1, 2, 3, then rewrite them in binary 0, 0, 0, 1, 1, 0, and 1, 1. I'll leave a quick binary primer on screen in case it's helpful. After you've numbered the squares with binary, you write down the binary numbers of all heads coins and ignore the tails coins. Then sum up each column individually. First column, 0 plus 1 plus 1 is 2. Second column, 0 plus 0 plus 1 is 1. If the sum of a column is even, write a 0 underneath. If it's odd, write a 1 underneath. Then this new binary number, 0, 1, gives us our encoded square under this arrangement of coins. Now I will take this arrangement, copy it 3 times, and flip a different coin on each. I want you to figure out and write down where the encoded square is for these 3 boards. Pause if you need to. If you did this correctly, you'll notice that each of these 3 boards created a different encoded square. If you flip 0, 1 to heads, this moves the encoded square from 0, 1 to 0, 0. Flip 1, 0 to tails, and it'll move from 0, 1 to 1, 1 instead. Flip 1, 1 to tails, and it'll move from 0, 1 to 1, 0 instead. With a single coin flip in each scenario, we're able to move the encoded square to any other square on the board. That's good and all, but how do you figure out which coin to flip to move the encoded square to a specific desired square? That turns out to be surprisingly simple. First, you figure out the encoded square. In this case, it's 1, 0. Then let's say the key is under 1, 1, so write 1, 1 underneath. Then compare these 2 binary strings. If a column is the same, write 0 underneath. If it's different, write 1 underneath. This is basically an exclusive OR, or XOR for short. The resulting number tells us that to move the encoded square from 1, 0 to 1, 1, we need to flip 1, 0. Then, if we reran the algorithm on this new layout, we now get 1, 1 as the encoded square. Success! Yay! Except you're not out of prison yet! The next step is to generalize this to the 64-square board. Instead of 2 bits, we now have 6 bits to represent each square. And this is the really neat part. The process will be the exact same with the same algorithm, only with 6-bit binary numbers. You might wonder if there's a visual way to interpret this process of finding the encoded square. And there is. It involves sectioning off the board into different halves. To start, if the number of heads in this half is odd, write down a 1 in the first digit. Otherwise, write down a 0. Then for the next digit, it's this half, then this, then this, then this, and finally this. And it turns out the output of this process is completely identical to our earlier algorithm. You might have noticed that the square of all zeros has literally 0 influence on the encoded square, and is the only coin that is in none of those visual groupings. Heads or tails, it'll never move the encoded square, and depending on your reading of the rules, could be removed from the board. If player 1 must flip a coin, then the 0 coin must remain in case the encoded square is already on the key square to begin with. But if player 1 merely has the option to flip, then we could remove this coin with no functional difference. To sum it all up, in order to solve this puzzle, player 1 takes the binary of all heads, sums up the bits, figures out the encoded square, and does an XOR against the key square to get the coin to flip, and flips it. Then player 2 does his collecting of the heads, figures out the encoded square, which is also where the key is. And there you go, now you're free. If you like that, consider subscribing, and thank you for watching.